In this video, we're going to talk a little bit about some examples for integration in higher dimensions and how to do iterated integrals. I'm just going to go ahead and jump right in with an example and kind of walk through a couple of different methods that you can use to take care of these kinds of integrals. So the example that we're going to start with today is a triple integral. We're going to have the integral from 2 to 4, the integral from 1 to 3, of the integral 4 to 6, of x cubed y squared z, dz, dy, dx. Okay, so before I kind of start talking about how we're actually going to approach this integral, I want to point out something that's really particular and important as we go through that you make sure that you note is that when we worked with a single integral, so like if we can kind of ignore the dy dx and only focus on this first integral on the inside and the dz, we can kind of think about the integral and the dz here on the end as being paired together. I often think of them as kind of like bookends. They're always, you don't have one without the other. And it's really important in this particular case that you always have, when you have your integral sign, that you have the corresponding dz, dy, dx, or whatever with it, because it's really easy to kind of start getting these mixed up, because it's very important that you keep them paired with their respective bounds, or dz, dy, dx. So like, for example, dz always will be paired with the 4 to 6 in this problem. The dy goes with the second integral here, like so, that 1 to 3. And then dx is paired with the 2 to 4. Is how that goes together. So kind of keep in mind that we're thinking about this as being an integral that's taken 3 times, where the inside dz goes with the inside integral there, the dy goes with the second one, and then the dx, the outer one, goes with the outer one there. So anyway, let's start talking a little bit about the mechanics of what's going on here. So there's 2 ways to approach this. The first method, we can split this up into a product of integrals that is sorted by variable. And okay, so how does this work? Well, why does this work? Well, notice that on this inside here, we're going to focus only on the integral with the dz first. Notice that we're taking the integral with respect to z. This means that the x cubed and the y squared are treated as constants, so they can come outside of that integral. So this becomes the integral from 2 to 4, integral from 1 to 3, of x cubed y squared, integral from 4 to 6, of z dz, and then we still have our dy dx. Okay, so okay, so now we've kind of simplified down that inside one a little bit. But notice also, though, that if we want to consider this whole integral right here, the integral that goes from starting from the second integral sign over to the dy, now we're integrating with respect to dy. Well, x cubed is just a constant when we're integrating with respect to dy. So we can further split this up a little bit farther, and we have the integral from 2 to 4, x cubed, integral from 1 to 3, y squared, integral from 4 to 6, z, dz, dy, dx. Okay. Well, now we've got all these kind of like stacked integrals together, and each one with respect to the other ones is constant. So like this right here, the integral from 4 to 6 of z dz, that results in just a number. So it is just a constant with respect to the integral with respect to y and the integral with respect to x. And the same idea applies for the integral from 1 to 3 of y squared dy and the integral from 2 to 4 of x cubed dx with respect to the other 2 integrals. So all I have to do now is just take these and kind of split them up. So we have the integral from 2 to 4, x cubed dx, integral from 1 to 3, y squared dy, and then the integral from 4 to 6, z dz. And now at this point, we have each integral in terms of only one variable, and you can integrate or evaluate as normal. And that's really pretty much all there is to that. However, there is some cases in which you're not able to split this up as a product of integrals because sometimes you can't split up the function that's in the middle here, right? In this particular instance, we were able to do it, but we can't always do that. Like suppose we're going to see an example later where we have x and y plugged into a sine. There's no way to split sine up with the x and the y in that particular case. So we're going to have to look at another way to tackle those kinds of problems. The second method then is going to be to work from the inside out of the integral. This always works. Kind of. And I'll tell you a little bit more about that in a second. So anyway, our integral that we started with looked like the integral from 2 to 4, integral from 1 to 3, integral from 4 to 6 of x cubed y squared z dz dy dx. And we can kind of treat this the same way that we would treat function composition in the sense that we can start from evaluating in the middle here and then just kind of working our way out. So we'll take this integral first, and then we'll take the next integral, and then we'll take the next one. So we notice that we still have the integral from 2 to 4, integral from 1 to 3. But now we're going to evaluate this inside integral here with respect to just z. So x cubed and y squared get treated as constants. And then we take the integral of z, and we are going to get 1/2 z squared. And then the important thing here is to remember that we still have to evaluate from 4 to 6, okay? dy dx, okay? So then our next step here would be the integral 2 to 4, integral from 1 to 3, x cubed y squared. Evaluate this guy from 4 to 6, and you're going to get 36 over 2 minus 16 over 2. That's just going to be equal to 10. So I can kind of rewrite this as pull that 10 out to the front. Oops, this should be an x dx. Okay, just like so. And now we just repeat that process. We're going to integrate with, or we're going to integrate the inside here with respect to y. So I've got 10 times integral from 2 to 4. X cubed gets treated as a constant because we're only looking at the y. And now we have 1/3 y cubed evaluated from 1 to 3 dx. So that's going to be 10 integral from 2 to 4 x cubed. Evaluating this guy right here, we get 27 over 3 minus 1/3 dx. And that kind of simplifies down to, you're going to get 260 over 3 out here in the front, integral of 2 to 4 x cubed dx. So it's 260 over 3 times 1/4 x to the 4th from 2 to 4, which is what we get from evaluating that integral. And then whatever 260 over 3 times 256. 6 minus 16, and then this is still times 1/4 out here. That came from there. So and you can throw that into your calculator and figure out what that is equal to. But you can use either method as long as either method is capable of working. But this one will work every time, again, with a little caveat that I'll tell you about later. Let's do another example. I'm just going to look at a little bit more simple one. We're going to have the integral from 1 to 2, integral from 4 to 5 of 2 dx dy. And this, first thing I'm going to do is pull that 2 out to the front because I can. So we have the double integral 1 to 2, integral from 4 to 5, dx dy. All right. Well, I mean, there's really nothing inside of here. We're not too worried about having to split up a function or anything like that. So we can actually go ahead and just split these into two integrals that are multiplied by each other. So we have 1 to 2 dy, like so. Because you want to make sure that we're keeping our, this guy stays attached to that one, and then the inside one stays attached to that one. So we have the integral from 4 to 5 dx, like so. Okay, So it's just 2 times y evaluated from 1 to 2 times x evaluated from 4 to 5. And that's actually just going to wind up giving us 2 at the end. But that's pretty much all there is to being able to split it up into 2 pieces like that and then evaluating it separately. I do want to show you an example, though, of when you like absolutely cannot split it into a product. So let's walk through that. In this particular example, we're going to take the integral from 0 to 1 over 4, integral from 0 to pi over 4, and then y sine of 2xy dx dy. Okay. So in this particular scenario, I mean, like in the last 2 examples that we've looked at, we've been able to split them up into pieces. But this particular one, we can't. So, but I mean, like we can a little bit, I guess. We can pull this y out to the front because this first integral in here is just with respect to x. So we have the integral from 0 to 1 over 4, y, integral from 0 to pi over 4, sine of 2xy dx dy. Okay. But we can't really split this up any farther, and we can't really pull the sign out because, I mean, I guess it wouldn't really get us anywhere even if we could. But because we're integrating with respect to x, anything that's got an x attached to it cannot pass through this integral sign here to the outside. So we're going to have to figure out how to integrate this inside here first, and then we'll use whatever we get out of this to integrate the whole thing. So cannot split. We will evaluate from inside out. All right, so what is that going to look like? Let me get a different color here. Okay, so we're just going to evaluate this integral first, and then we'll use what we get out of that to evaluate the next one. Okay, so we have sine with a function plugged into it, and that means that we are going to want to use u substitution. Just like kind of actually same idea as working with partial derivatives, we can use a lot of the same integration rules that we did when we were working with one variable at a time, because when we're working strictly inside of this integral with respect to x, y is now getting treated as though it is just a number. So we're going to use u sub, and we're going to set u equal to 2xy. And this means then that du is equal to 2y dx. So remember, y is just a constant inside the integral with respect to x. Okay, so, well, I don't have 2y dx here. I just have dx. So the dx that I'm going to use is going to be, we'll have 1 over 2y du is equal to dx. So that's what I'm going to use for my substitution. So my integral from sine of 2yx dx is equal to the integral of 1 over 2y sine of u du. Remember that y is just a constant. I'm going to take that integral there. I'm going to get negative 1 over 2y cosine of u. Cool. I want to substitute back in this 2xy, so I get negative 1 over 2y cosine of 2xy. Okay. Notice that I didn't really worry too much with my endpoints here with u sub. My personal preference is to just go through, do the u sub, and worry about endpoints at the end. So that's what we're going to do now, is we'll mess with the endpoints now that we're looking at substituting this back into our integral. So this is all equal to, this whole thing here is all equal to the integral from 0 to 1 over 4 y times our newly computed integral here. We got negative 1 over 2y cosine of 2xy, and this is all evaluated from 0 to pi over 4. I really want to emphasize, and maybe I should have said this on the last example, or the first example, I guess. that this 0 to pi over 4 is only getting plugged into x, okay? We're not plugging it into y because this came from evaluating the integral with respect to x. This only gets plugged into x. All right, so I also want to point out that we have this really nice thing here that these y's are going to cancel out, so that's pretty great. Anyway, we're going to get negative 1/2 integral from 0 to 1 over 4 cosine of pi y over 2, and then minus, it's going to be cosine at 0 is what we're going to get there, and that's just going to be 1. And then at this point, you are able to evaluate this integral as normal, and I believe that the answer that you're going to get will be 4. So yeah, at this point you would just still use, I mean, like I guess a u sub all over again, but this time you wouldn't have an x floating around in that as well. So that's pretty much all there is to that, though. This idea of working from the inside out is really quite nice. It's typically the one that I wind up using, but being able to split up the integral into products also comes in handy later. So, but we'll talk about that a little bit more in the future. So now, I did say that working from the inside out came with a caveat, and that is in the sense that sometimes you have to do some rearranging before you're really able to do that, or before that becomes the optimal solution. And that comes in the sense of being able to change the order of integration, right? So we want to talk about that just really quick. Changing order of integration just means that we are able to interchange which order we take the integrals in. So for example, if we're doing the integral from say 0 to 3 and the integral from 1 to 4 of x squared y dy dx, this would be the same thing as taking the integral from 1 to 4, integral from 0 to 3, x squared y dx dy. Oops, y. So these are exactly the same value. I won't compute this integral for you, but we are allowed to swap the dy and the dx as long as we keep the ends or the bounds of integration matched up. Okay, so again, remember that it's very important that we keep these guys paired together, like so. And you can do this anytime you want. You're welcome to do that as much as you want. But there comes some times that you actually really want to do that before you start integrating. And I wanted to show you an example that's a little bit more complicated and would lend itself best to this type of setup. So in this particular example, we will change the order of integration so that way it's easier to evaluate. So in this one, we have the integral from 0 to 3, integral from 0 to 2, y squared sine of pi over 2 xy dy dx. Okay. Well, first of all, since we have x and y inside of sine, we can't split this as a product. Okay. We are allowed to pull the y squared out to the front. That would be fine, or at least outside of. Well, not yet anyway. That's coming later. But we've got all this right here. And if we evaluate with respect to y first, we take this integral. The way that we're going to have to do this is to use integration by parts. But since y is squared, it will not suffice to do integration by parts once. We're going to have to do it twice. And that gets kind of messy and it's tedious and time consuming. And honestly, most people don't really find that to be a good time. So what are some ways that we could kind of rearrange this to make it so we're not able to have to, or so we don't have to do integration by parts twice? Well, we notice that this is a very similar setup to the last problem that we did, right? So if we were, able to pull the y squared out to the front, do u sub on sine, maybe we'd lose a y and then we wouldn't have to do integration by parts twice. Well, we can pull the y squared out to the front if we were integrating with respect to x and not y. And we can make that happen by changing the order of integration. And that's exactly what we're going to do here. So we're going to have the integral from 0 to 2, integral from 0 to 3. y squared sine of pi over 2 xy. Now we have dx dy. Okay, so all we've done is we've swapped the order that we're going to do this problem in. And what this means is I can pull the y squared out to the front here. So we have the integral from 0 to 2, y squared, integral from 0 to 3, sine of pi over 2 xy dx dy. Okay, so now all I have to do is deal with this inside integral here, which is a simple u sub, actually almost identical to the one that we just did. And then after that, we'll have a y cancel out. So what we're going to get is integral from 0 to 2. Taking care of this integral right here, what we're going to get is we have the y squared still times 2 over pi y times negative cosine of pi over 2 xy. And now we're evaluating from 0 to 3. Just like so. And going from this line to this line uses exactly the same process as what we just did earlier. So I'm going to evaluate this and then also kind of simplify things down a little bit. I'm going to get negative 2 pi here in the front, integral from 0 to 2. I'm going to lose this y right here and the squared off of that y. So now I just have y times cosine of, it'll be 3 pi over 2 times y. 0 goes in for the x. I'm going to have cosine of 0, which is just 1, dy. Okay, so that's negative 2 pi integral from 0 to 2 y cosine of 3 pi over 2 y minus y dy. And I'm going to break this down even farther. And what we get is negative 2 over pi integral from 0 to 2 y cosine of 3 pi over 2 y dy minus the integral from 0 to 2 y dy. And then close that parentheses because the negative 2 over pi has to go across the whole thing. This piece right here, quite simple. That's just 1/2 y squared evaluated from 0 to 2. Piece of cake. This piece right here is going to take integration by parts. I'll walk through that in case you're a little bit rusty, but it's exactly, it's just a y. There's only, it's the only variable there. Exact same process as what you learned in Calc 2. So let's go through that. Looking at this here, we remember that integration by parts tells us that if we have the integral of u times dv, this is equal to uv minus v, or the integral of v du. So I have to find my u, I have to find my dv in this thing right here, and then I have to compute that piece there. General strategy for finding u is you want the thing that when you take the derivative, it'll disappear. Taking the derivative of y will make it disappear. Taking the derivative of cosine will never make it disappear. So u is going to be equal to y. So du is equal to dy. And then dv is what's left over. So dv equals cosine of 3 pi over 2y dy. And then all I got to do is integrate both sides there, and I get v is equal to 2 over 3 pi sine of 3 pi over 2y. And then I just have to plug all these pieces into this expression right here. And so I'm just going to do that here in the next line, kind of combine it all together. I'm going to get, this is equal to negative 2 over pi times u times v. So I'm going to have y times 2 over 3. Oops. 2 over 3 pi. No pi up there. Sine of 3 pi over 2 y minus the integral from 0 to 2. 2 over 3 pi sine of 3 pi over 2y, and then dy is just going to go in for my du. And I do want to point out something that's very important and very easy to forget and get yourself turned around on. This had bounds. Anytime your integration by parts had bounds on it, this uv, you can consider it as having already been integrated, and now it just has to be evaluated from 0 to 2. Okay, so that's this integral right here. that still has to be evaluated. And then we also have to add in, or I guess subtract off, this minus 1/2 y squared evaluated from 0 to 2. And then that's pretty much it. This piece right here gets evaluated as normal. And this piece right here is just really pretty much some plug and chug. So at the end of all of this, what you should get is 2 over pi, 8 over 9 pi squared, plus 2. And yeah, that's really pretty much all there is to that. So it's really not that bad. Once you recognize that changing the order of integration can make your life a whole lot easier. Otherwise, we would have had to have gone through this process twice to get rid of y squared. So you can always, always, always work from the inside out to evaluate your integrals. Sometimes it's easier to just split them up into products and do it that way. And sometimes you have to do it that way with the integral from the inside out, and then change the order of integration if need be to make it easier to work with, or even just possible to work with. So anyway, I hope this was helpful. In the next video, I'm going to talk a little bit about generalizing average value of a function to higher dimensions. So I'll see you then.